welcome back to this session. In addition to the tutorial, there were some questions, so I'll try to answer some of them. Now, one question was, yesterday we found the pressure distribution in a fluid where the density was constant. So the question is, what happens when the density is varying? Now, when the density is varying, the fluid may or may not be at rest. So let us look at then the condition under which the fluid can be at rest. Okay. So we'll look at necessary conditions for what you may call hydrostatic equilibrium. All right, so what we'll do is we'll assume that the fluid is at rest. That is, it can remain at rest. So we'll assume that the fluid can be at rest. Then the pressure distribution we found is obtained by solving this equation, grad of P equal to rho g. Now, as we go further in the course, we will derive the equations of motion, and you will see that there will be other terms when the fluid is not at rest. Okay. Now, suppose I start with this, assume that this is correct, and take the curl of both sides of this vector equation. So if I take curl of grad P, this should be equal to curl of rho g. Now, what is curl of grad P? Can you give me an answer? Yes, no, using your tablet. Is it 0 or non-zero? This is? Well, you can look at it this way. This is ijk, then grad you view as a vector operator, del x, del y, excuse me, del z. Then grad P has elements del P del x, del P del y, and del P del z. Now, if you look at the I component here, you have del del y here operating on del P del z, and del del z here operating on del P del y. So, you are going to have del 2 P del y del z minus del 2 P del z del y I plus two similar terms. Now, if P is a continuous function and del P del y are also continuous, then you know that the order of this mixed derivative does not matter, that these two are going to be equal. So, you are going to get here 0. And similarly, the other things will be 0. So, curl of grad P you know is 0. Now, let us look at what is curl of rho g. So, this is given by this determinant. You write in the first row ijk. Then as for any cross product, you will write the elements of the first vector in the second row and the elements of the third vector, the second vector in the third row. So, here you are going to have del del x, del del y, del del z, and then you will have rho gx, rho gy, and rho gz. Now, for simplicity, let us take a coordinate system where z is vertically upwards. So, the gravity vector is in the minus z direction. So, this is x and this is y. So with reference to this coordinate system, your gx and gy are 0, and your gz is minus g because it's downwards. So if you look at it this way, you're going to have minus del y of rho g I. So g is minus gk. So if you look at the I component, you have del y operating on, this is minus rho g, the third term. And then if you look at the k component, that is 0 because both of these are 0. And if you look at the j component, you're going to have this subdeterminant, so plus del x of rho g j. Now when I looked at this vector equation, we showed that the right hand side is identically 0, curl of grad phi. Now suppose the right hand side here, curl of rho g, which is given by this, is not 0, then there is a contradiction. So that means that if the density variation is such that this quantity and this quantity are different from 0, then the fluid cannot be at rest. So a necessary condition for the fluid to be at rest is that this is 0 and this is 0. Now in most cases g will be constant, so I can pull it out over here, write it as minus g into del rho del y I, and this will be plus g into del rho del x j. So that means that curl of rho g will be 0 when del rho del x is 0 and del rho del y is also 0. That means there should be no horizontal gradient in the density. So del rho del x must be equal to 0 and del rho del y must be equal to 0. When these two conditions are satisfied, then curl of rho g is 0 and the body force can be balanced by the pressure, and then the sum of the forces will be 0 and there will be no acceleration. The fluid will remain at rest. So rho can be a function of z, where z is the vertical coordinate. So if I say this is x, y, z and g is downwards, if the density varies vertically and is not a constant, some arbitrary function of z, then you can have a hydrostatic equilibrium where to get the pressure distribution you solve this equation dp dz is equal to minus rho of z into g. But if the density varies in the horizontal direction either with x or y or both, then the fluid will not remain at rest. So we will not be able to find the pressure distribution in this way. Now you have got the tutorial sheet. There is one problem, I think it's towards the end, where the density variation is given. So you can try and solve that and see how to solve this differential equation as an example. problem
9 reads that this is the problem number 9. You can see, I'll mark it. So under some conditions, the atmosphere is adiabatic, where pressure is given. The pressure is pressure and density relation is given, which is something like this. You can see, E is equal to C rho to the power k, where k is the specific heat ratio and C is a constant. K is the specific heat ratio and C is a constant. Show that for an adiabatic atmosphere, the pressure variation is given by something like this. So an expression is given, we'll have to prove it. So let us try to do that. So we have the basic equation, which is dp dz equal to minus rho of z into g. Now rho is of course a function of pressure here, as given here in the problem, as written here. and this pressure is expected to vary in the vertical direction because of the presence of gravitational force or the body force. So that means rho will be a function of z, since it's a function of pressure, and pressure of course is a function of z, as is very evident from this equation. Now so what we do is we try to express this equation in terms of pressure and z only. Since we have to obtain the pressure, so we need to convert this rho, we need to write this in terms of pressure, which we can write from here. So this we can write as rho equal to P by C to the power 1 by K. So that, let us substitute rho here. So we'll do that. So we'll write minus, that will be minus P by C to the power 1 by K into G. So let us bring P in on this side and Z will bring on this side, because C and G are constant here. So we can write dP by P to the power 1 by K equal to minus G by C to the power 1 by K dz. So we will integrate it now. So if we integrate this, so we'll integrate both sides here. So so this integral turns out to be nothing but e to the power minus 1 by k plus 1 by minus 1 by k plus 1, and the left hand side and the right hand side takes the form g by sorry, there is a minus sign, g by c to the power 1 by k into z plus some constant. So let us call this constant a. So this we can simplify, the left hand side we can simplify as p to the power k minus 1 by k. So this reads like this, equal to a minus g by c to the power 1 by k into z. Now we need to determine this constant a here. Now this constant we can find out from some kind of boundary condition. As the boundary condition, we look at the problem, and if we can see that there is some pressure P naught given here. So this P naught is nothing but the atmospheric pressure at the sea level, that is at z equal to 0. So we'll assume that at z equal to 0, so at z equal to 0, we'll assume that P is known, which is nothing but P naught, and we'll also assume that temperature is known, which is T naught. So you can see P naught and T naught both are given. These are constants here. So we'll assume that at z equal to 0, P pressure is equal to P naught, which is nothing but the atmospheric pressure, and T equal to T naught, which is again temperature at the sea level. So P equal to P naught and T equal to T naught. Okay, so let us put this condition in this equation, and we get, so we will put z equal to 0. So we'll get k P naught to the power k minus 1 by k minus 1 equal to a. So we now know the constant, right? So we can now put this value in place of a here, and we can write this equation in this form. So k e to the power k minus 1 by k minus 1 is equal to k P naught to the power k minus 1 by k minus 1 plus minus g by c to the power 1 by k into z. So we will now divide both sides with this term. Divide both sides with this term, and we can write finally 1 minus this k minus 1 by k to the power 1 by k P naught to the power, this is k minus 1 by k. So I have taken common this term. So now we take take the root, this root. So we take this root k minus k by k, this 1 minus 1 by kth root of this equation, and we end up with so this becomes 1 then. If we take this root, if we take this root, this becomes 1, this becomes p only, and this becomes p naught, and this will 1 minus g into that is, this will be a by a minus 1. So we need to prove this. We have already got this term here, the power. So we need to somehow relate this C with temperature. So now we use the ideal gas relation. The ideal gas relation, because we'll assume here the air is an ideal gas. So if we now write the ideal gas equation, it's simply P equal to rho R T. This R is not the universal gas constant, but this is R bar. If we call R bar as the universal gas constant, then this R is R bar by M, where M is the molecular mass of air. This is that R. So that is equal to R here. So if we do that, then we can write that, and we can also use this relation, the pressure and density relation that is given here, and we can write density equal to rho equal to, as we wrote here, this relation, P by C to the power 1 by K, that is equal to P by RT. So now we know that so now we apply this condition here. At the ground, it is at Z equal to 0, P is P naught and T is T naught. So here we replace this P with these two P's with P naught, and this T we replace with T naught. So if we do that, we'll find P naught by C equal to the power 1 by K is equal to P naught or T naught. So that means here we can write 1 by C to the power 1 by K equal to 1 by RT naught. This we can write, right? So I've just brought this P on this side and brought this P on top at the bottom. So we end up with this kind of relationship of P. Just adjust the powers of P, and this is C to the power 1 by K. So we have this expression here, this equation. So as we can see, we have an expression for this from here, right? We can simply replace this 1 by C, this term, as it appears here, with this 1 by RT naught. So if we do that, we'll find, I'm sorry, this not this one, in this equation. Sorry, not in this equation. Now you can also replace it here and here also. So we'll do it here. Here we can do that. So if we do that, we'll find E naught 1 minus G into A minus 1 Z by K R. This 1 by C to the power 1 by K into P naught to the power K minus 1 by K. This term is 1 by RT naught, as you can see from here. So we'll simply replace it that with this, and the power will of course be. So we have derived this relation, that P as a function of Z, which we obtain as this. So we have proven the relation that has been asked. No questions. Okay, thank you.
Now let us look at what may be called relative hydrostatic equilibrium. I will consider a container which is partly full of a liquid. Let us say I have a rectangular container and you have water up to this level. So this is the direction of gravity. You know that if it is at rest, this surface will be horizontal. Of course, there may be some surface tension effects which we are not looking at over here. So there will be an angle of contact over here. So let us say you have water in the tank and air above. Now suppose I apply a impulsive force to this and start to accelerate it. So the container moves to the right, and we'll consider a situation where the acceleration of the container is constant. So if A is the acceleration of the container or tank, whatever you call it, A of the tank is constant. Now the moment you start pulling this tank to the right, the free surface, which is the interface between the water and the air, it will not remain horizontal, but it will start to oscillate. Eventually the oscillations may die out and the fluid may reach an equilibrium state where the fluid particles are at rest relative to the container. The container may be moving and the fluid particles are also moving with the same velocity. In that case, the acceleration of the fluid particle will simply be the acceleration of the tank. And then you can find what is the pressure distribution. Now you have to modify your equations. You are going to have mass times the acceleration of a fluid element. You can say its average acceleration is the net force. The net force, you know, there are two types. One is the body force, the other is the surface force. Net. So I can take a fluid particle here or element of fluid similar to what we did last time. Only thing now, yesterday we had the left hand side equal to 0 because the fluid was at rest. Now it is moving. Now this mass we can write as the average density rho star into the volume of this element, and this is the average acceleration. The body force similarly is mg, which is rho star v into g, and then you are going to have this net surface force, which is going to be the force due to the pressure. Now what we will do is we will divide this whole equation by V. Then we will have rho star A star is equal to rho star G plus this net surface force divided by the volume. Now we will take the limit V going to 0. Now when you take the limit V going to 0, this rho star, the average density, will become the local density. This average acceleration will become the acceleration of the particle, and this side will be again rho, and this is the acceleration due to gravity, which we are taking to be constant, and this quantity we have seen last evening as minus grad of P. So when we looked at the basic equation of hydrostatics, the left hand side was 0. We had rho g minus grad P equal to the 0 vector. Now we have this additional term, and if you want, you can write A as the material derivative of V, which was covered this morning, and that will give you the equations of motion for a inviscid fluid. Now we are considering a case where after this fluid surface oscillates, the oscillations will die out. There is a transient period when the oscillations are damped out, and eventually the acceleration of the tank will become a constant. The acceleration of the fluid particle will be the acceleration of the tank. So you are going to have this equation grad P equal to rho g minus A. I moved this grad p to the left hand side and the a to the right hand side. And this a will be the acceleration of the tank, which we are taking to be a constant vector. So I'll draw that figure again, this side, and I'll show by dotted lines the level of the liquid when the tank was at rest. Now let us say the acceleration of the tank here is say 1 meter per second squared into I, let us say. We have a stationary coordinate system here, xy. Now the equation which we are going to solve is grad p is equal to rho into g minus a. Now once the oscillations of the free surface have died out, that oscillation of the free surface is what is called sloshing. Once the sloshing has died out, it will reach an equilibrium state where this free surface will not be horizontal but inclined. Now we would like you to tell us which is the correct equilibrium situation. One is A is this, B is this, and C is this. So we would like to test out the Akash tablets which were given to you. So can you give the options A, B or C? Using your tablets. Board দিতেই হবে। মানে ফোন না হলে হবে না। হ্যাঁ আচ্ছা D, none of the above. So I think you are getting 4 options. Time 1 minute. So we want to know which is the correct equilibrium state, A, B, C or D, when the acceleration is a constant to the right. ওরা বুঝে যাবে কমের টাইম। আচ্ছা ঠিক আছে। So মানে all right, now see this right hand side is a vector, G is downwards and A is to the right, so minus A is this way. So So if you add G and wave vectorially using the triangle law, you have a vector which is like this. So this is the G minus A. Excuse me. Now rho is a scalar, so if you multiply G minus A by rho, it is going to be another vector in this direction. And this is going to be equal to grad P. Now you know from your vector calculus that grad P at a point is orthogonal to the surface of constant pressure. So if you look at the surface of constant pressure, they are going to be perpendicular to this line. So this is say excuse me, P equal to A1, P equal to A2, P equal to A3. So this could be 1, 2, 3, whatever it is. Now this free surface is a surface of constant pressure, so it will be like this. So the correct answer is B.
The tutorial sheet question number 3. Please read the question. Small differences in gas pressures are commonly measured with a micromanometer of the type illustrated in figure 3. This device consists of two large reservoirs, each having a cross-section area A, which are filled with a liquid of density ρ1 and connected by a U-tube of constant cross-section area A containing a liquid of density ρ2. When a differential gas pressure P1 minus P2 is applied, a differential reading H develops. Determine the relationship between H and P1 minus P2 and the ratio is small. So suppose there are the pressures here and the pressure here are equal. In that case, the liquids will maintain a same level in both the vessels. So this vessel has an area capital A and this tube has an area small a. It is given that A is much smaller than the reservoir area. So in case of equilibrium, all the levels, so the hatched is ρ2 and the dotted is ρ1. Right? So if there is a differential pressure, that is P1 is greater than P2, then the level in the left hand side reservoir will decrease. So if this level decreases, this level will be pushed up, as a result of which liquid in this limb will increase. Okay, this is pretty clear, right? So it is given that this decrease in the level is delta and this increase in the height is h. We are supposed to find out an expression for P1 minus P2 when this happens. So when P1 is greater than P2, we will quickly draw the equilibrium diagram when it goes into equilibrium. So this difference in heights between this level and this level is delta, and this difference in the level is h. So the pressure at these 2 points, I denote them by A and B, have to be equal in equilibrium. So if I write down the expression for the pressure at A, it would look something like this. So the pressure P1 is acting on this. So P1 plus, if I denote this height by say alpha, so P1 plus alpha into rho 1 GH. Is the pressure at point A. The pressure at point B will be P2 plus, so since this is alpha, this height will be alpha plus delta, right, because this is delta over and above alpha, and this height is small h. So this height will be alpha plus delta minus h. Okay, so this will be the pressure at point B because of the contribution from P2 from the liquid of density rho 1, which is this, and the liquid of density rho 2, which is this. Fine. So this term and this term will get cancelled, and if I take P to the left hand side, the task is to relate what this delta and how this delta and this H will be related. Now whenever the liquid is pushed down in the reservoir, an equivalent amount of volume will rise up in the smaller limb. Okay, so the volume that is pushed down will be equal to delta into the area of cross section. So from basically this is an equation of continuity. So the volume pushed down in the bigger reservoir is equal to delta into capital A. The area of the reservoir, big reservoir, is capital A, and the area of the limb is small a. So the volume pushed down is delta into A, which is equal to the volume pushed up. Because the liquids are incompressible, the same amount of volume will be pushed up in this in the limb. That will be equal to H into small a. So from this, the rise delta is equal to H times A by capital A. Substitute delta from equation 2 in 1, P1 minus P2 will be equal to Hg rho 2 minus rho 1 plus Hg rho 1 A by small a by capital A. It is given that small a by capital A is much less than 1 because it is mentioned here that the ratio A by A is small. So if we neglect this, P1 minus P2 is approximately equal to GH rho 2 minus rho 1. Any questions? So there is another question here asked. It is desired to have this reading sufficiently large for small pressure differentials. Why? So when there is a differential pressure acting on the two limbs, you get a reading H. You want this reading H to be large. Now, can anyone tell why this should be like this? In the question it's mentioned, right? When there's a differential pressure acting on the two limbs of the manometer, there's a pressure differential obtained because this liquid is pushed down, as a result of which there will be liquid pushed up in the limb. So in order to measure small pressure differentials, you ideally want a large H because the device sensitivity is defined that way. If for a given pressure differential you don't have a very large H which you cannot measure, you won't be able to measure the difference in the pressures. So if you have a large H for a small pressure difference, you are able to measure the small pressure differences by measuring a sizable amount of H. That is the principle.
Now let us consider another case where we have a cylindrical tank so this is the central line. We will consider a tank which is mounted on a turntable, and initially let us say you have water up to this level or some other liquid and you have air on top, and you start rotating it about its own axis with a constant angular velocity omega. Now in this case what happens is after a certain time has elapsed, the fluid will rotate as if it's like a rigid body. Now if I take a coordinate system with z axis upwards, and here you can take either a cylindrical or a Cartesian coordinate system. So we will put the origin here. Suppose I say this is x. Now I will show the other view. So if you look on from the top, you have a circular tank, and this is my x in the horizontal plane, and this is y. So z, the gravity is this way. Now most books will do it in cylindrical coordinates. So if this is the origin, if you have a point here in the horizontal plane, if this is the radius r, this angle will be theta. Now here the acceleration of the fluid particle is the centripetal acceleration. So we are going to have minus omega squared r into what we may call ER. ER is the unit vector in the radial direction. So this is your ER pointing radially outwards, and if you look at the one perpendicular to this, that you may call E theta. Now you can see that ER is a unit vector, so we are using this caret sign or hat sign to denote unit vector. So this length is 1 and this angle is theta. So this is cos theta I plus excuse me, sin theta j. So the acceleration, if you want to use the Cartesian coordinates, you can write as from here minus omega squared r cos theta I plus sin theta j. Now if we drop a perpendicular here, this is x, which is r cos theta, and y is r sin theta. So you can either use Cartesian coordinates x, y, z or cylindrical coordinates r theta and z. We see that r cos theta is x and r sin theta is y. So this is minus omega squared x I minus omega squared y j. Now once again the equation which you will solve to find the pressure distribution is grad of P is rho times A minus G. Now according to this coordinate system, your G is minus G K. I'm sorry, it is rho of G minus A. Now I can write this as then rho of minus gk plus omega squared x I plus omega squared y j. So if we equate the left hand side of this, the I components, j components and z components, k components with those here, we are going to have del p del x equal to rho omega squared x, because grad p x component is del p del x. Now grad p y component is del p del y. If we equate the y components here, we are going to have rho omega squared y, and the z component of grad p is del p del z, and the z component of the vector on the right hand side is now minus rho g. So I have to integrate these three equations to find the pressure distribution. So let me write it again on the next sheet and continue. So we have del p del x is equal to rho omega squared x. Now if I integrate this, we will get p is equal to rho omega squared x squared by 2 plus some function of y and z. So the best way to view it is take this expression and differentiate partially with respect to x. So you will get d dx of x squared is 2x. So half and the 2 will give you rho omega squared x, and the derivative of this partial derivative with respect to x is 0. Now if you look at del p del y, from here it is going to be del f1 del y, because the derivative of the first term is 0. Now this must be equal to rho omega squared y, which is the expression you had previously, this one. Now this one can be integrated to find what is f. f1 will be rho omega squared y squared by 2 plus another function, but this will be a function of z only because f1 depends on y and z. Now to find f2, we will have to look at the third equation to find. Okay, before that you can write p as, by substituting this over here, rho omega squared by 2 x squared plus y squared plus f2 of z. So if you want del p del z, that is going to be simply d of f2 dz, which must be equal to minus rho g. So we have made use of the first two equations. Now we look at the third equation, and if we integrate this, you get f2 is equal to minus rho gz plus, now you have a constant rather than a function because this is a total derivative. So if we go back and substitute over there, we have p is equal to rho omega squared by 2 x squared plus y squared minus rho gz plus a constant. Now if you want to switch to polar coordinates, r is the radius, so r squared is x squared plus y squared. From here also you can see, if I square x and y, it is r squared cos square theta plus sin square theta, which is 1. So you can come back here, and this is what you will find in most books, that p is equal to rho omega squared r squared by 2 minus rho gz plus c. Okay, now let us see what is the shape of the free surface. I will give you 4 options. One is, A is this, B is this concave thing, C is this, and D, let us say, is none of the above. Now let us again test your tablets. So please give your options. Of the free surface is P is equal to PA or P atmospheric, which is a constant. Now what we found was P equal to rho omega square r square by 2 minus rho gz plus constant. So P is equal to rho omega square r squared by 2 minus rho gz plus C equal to PA. This is the equation of the free surface. So I can write it as rho gz is equal to rho omega square by 2 r squared plus C minus PA, or Z is equal to omega squared r squared by 2g plus C minus PA by rho g. Now you see that if I look at dz dr, this is omega squared by g, which is positive. So if you look at the slope here, this one has positive slope and this one has negative slope, and this one has 0 slope. So this is the correct answer.